Welcome back, everyone. This is Conley, and tonight we're revisiting one of the most discussed aviation stories of the year, the tragic loss of UPS, Flight 2976, an MD-11 cargo jet that went down shortly after takeoff from Louisville, Kentucky, bound for Honolulu. In the weeks since, the NTSB and FAA have been carefully piecing together what happened during those final seconds, and new findings are starting to emerge. What follows is not speculation, but a methodical retelling of what we know so far, built on official data, engineering insight, and respect for the people who were on board. The aircraft involved, tail number N259UP, was a McDonnell Douglas MD-11 freighter, a stretch derivative of the DC-10 with a 206-foot wingspan and a maximum takeoff weight exceeding 650,000 pounds. 3 high-bypass turbofan engines powered at 2 under the wings and 1 embedded in the tail. On that afternoon at 5:15 p.m. local time, the jet lined up on the runway in clear weather, the sun beginning to dip low over Kentucky. Takeoff thrust pushed more than 180,000 pounds of total force through the pylons and airframe routine numbers for the MD-11, but still an enormous mechanical ballet that depends on every bolt performing perfectly. Moments later, witnesses along the airport perimeter saw something they couldn't quite process. As the jet accelerated, one of its engines, the number 1 engine on the left wing, a General Electric CF680C2, rated at over 60,000 pounds of thrust, detached completely from its mount. The pylon-to-wing interface sheared away, sending the engine sliding backward and twisting off under the wing. Flight data recordings and early cell phone video confirm what followed. The aircraft pitched left, losing lift on that side, asymmetric drag pulling it further until the nose dropped. Just beyond the end of the runway, it struck terrain, broke apart, and erupted in flame. The debris field stretched nearly half a mile, scattering cargo containers and aluminum fragments across industrial buildings near the airport fence. By sunset, FAA on-scene investigators had cordoned off taxiways and shut part of the field, while emergency crews fought lingering fires. It was immediately clear that this was not a routine engine failure. This was a structural separation, one of aviation's rarest and most feared malfunctions. The NTSB's preliminary statement confirmed that the left-wing engine had separated during the takeoff roll. The focus turned to that pylon and to a single question that would define the investigation. Why did it let go? For those of us who've spent years around big jets, the connection between an engine and the wing isn't just metal, it's a symphony of physics. The pylon must absorb thousands of torque cycles, vibration, harmonics, and thermal expansions over decades. The MD-11, like its DC-10 ancestor, carries each underwing engine on a forged aluminum alloy fitting, secured by 1-inch diameter shear pins and bolts rated to withstand more than 100,000 pounds of load. Over time, however, microscopic cracks known as high-cycle fatigue fractures can form in these fittings. Each takeoff, each pressurization, flexes the joint just enough to grow those cracks atom by atom. Normally, rigorous inspection schedules catch them long before they become dangerous, yet fatigue has a way of hiding until the moment forces line up just wrong. Investigators immediately began examining possible triggers, loosened hardware, corroded pins, or resonance mismatch that could have produced stress oscillations during spool-up. On a trijet like the MD-11, those engines deliver asymmetric gyroscopic loads as they spin up from idle to 90% power. If one mount isn't seated perfectly, the vibration can magnify at frequencies around 50 Hz, right where the structure is most vulnerable. One theory under review is that a small pre-existing crack in the aluminum pylon fitting propagated suddenly under that stress, releasing the entire assembly. It's a haunting echo of history. 46 years earlier, on the 25th of May, 1979, American Airlines Flight 191, a DC-10, lifted off from Chicago O'Hare with 271 people on board. 31 seconds into the climb, its left engine and pylon ripped free, vaulting over the wing at 300 feet per minute. The jet rolled left, inverted, and crashed within seconds, killing everyone aboard and 2 on the ground. To this day, it remains the deadliest single aircraft accident on US soil. Back then, the NTSB uncovered a disturbing maintenance shortcut. Facing economic pressure after the oil crisis, American Airlines had replaced the factory-mandated engine removal process, which required detaching the engine separately using a crane, with a faster method using a forklift to remove the entire engine plus pylon assembly. The forklift slipped during reinstallation, striking the wing's forward bulkhead and misaligning the pylon by half an inch. Small cracks formed around the clevis pinholes, invisible to casual inspection. When the aircraft flew again, those cracks grew until the pylon failed catastrophically on that May morning. Congressional hearings later blasted the airline for cutting maintenance from 68 man-hours to 26, prioritizing turnaround speed over safety. The FAA admitted it had approved procedures without full stress testing. In the aftermath, every DC-10 inches the United States, all 273 of them, was grounded. Engineers redesigned the pylon with stronger aluminum, added redundant shear pins, and mandated X-ray and dye-penetrant inspections of bulkhead fittings. The redesign improved overload tolerance by 150%, introduced spherical bearings to distribute forces evenly, and installed electrically actuated slat locks so a detached engine could never again retract a wing's leading edge slats and rob it of lift. The system's hydraulic pressure, once a single circuit, was re-engineered into backups capable of 3,000 pounds per square inches, each a triple redundancy that later carried into the MD-11. The MD-11 entered service in 1990, marketed as the DC-10's safer, more efficient successor. It stretched the fuselage by 192 feet, refined the aerodynamics, and retained the tri-jet layout with the choice of CF6 or PW4000 engines, producing up to 93,000 pounds of thrust. Each pylon was reforged in titanium with crack-arresting doublers and vibration isolators tuned above 50 Hz. The design added elastomer dampers to absorb gyroscopic torque and used AI-based load modeling long before the term became common. Most importantly, the aircraft featured 3 independent hydraulic systems, any one of which could control the plane in an emergency. By the mid-2000s, the MD-11 fleet had logged over 10 million flight hours, with dispatch reliability above 99%. That record is why this UPS accident shook so many professionals. When a platform with decades of safe operation suddenly fails in a way reminiscent of its 1,970 seconds ancestor, engineers take it personally. Could metal fatigue after 75,000 flight cycles have escaped detection? Were existing ultrasonic scans sufficient? Or had years of service gradually outpaced inspection intervals that were once adequate but now outdated? As the NTSB gathered fragments of the left-wing pylon, specialists began electron microscopy analyses to read the metal story. Under high magnification, fracture surfaces revealed distinct patterns, a granular texture if torn by overload, or smooth beach marks if grown slowly through fatigue. They can even count the number of stress cycles that produced each ripple. Every bolt, washer, and shear pin from the wreckage is now cataloged and will be stress tested to its breaking point. Meanwhile, FAA engineers on site examined maintenance logs provided by UPS, a company widely regarded for its stringent safety culture. Those logs included recent torque verifications, thermographic scans, and even AI-monitored vibration data. Nothing obvious, yet pointed to negligence. Still, investigators know that age introduces subtle problems: corrosion between dissimilar metals, sealant breakdown, and tiny fretting motions invisible to the naked eye. Comparisons between the two tragedies reveal both chilling parallels and crucial differences. Both involved McDonnell Douglas tri-jets, both lost their left engines during takeoff, and both suffered asymmetric lift that led to an uncontrollable left roll. In each case, the pilots were past V1 decision speed, roughly 150 knots for the DC-10, a bit faster, around 160 knots, for the MD-11, meaning aborting the takeoff was no longer possible. They were committed to fly. Once the roll began, the aerodynamic forces overwhelmed any corrective input. Yet, unlike Flight 191, early evidence from UPS 2976 shows no total hydraulic failure. The MD-11's redundant systems appeared intact up to the moment of impact, Instead, analysts suspect secondary wing damage, compounded by a compressor stall in the tail-mounted number 2 engine, possibly triggered when debris from the detached pylon was sucked into the intake. Video frames indeed show a burst of flame at the tail seconds before the crash, consistent with a stall. That distinction matters. It suggests the redesigned hydraulics performed as intended, but other physics took over too quickly to recover. Understanding those seconds is more than academic. For engineers, it determines whether the failure was isolated or systemic. For pilots, it's a reminder that training and hardware must evolve together. The NTSB's timeline projects a 1-2 to 1-8 month investigation before a final report, a period that will include microscopic fracture mapping, 3D stress modeling, and simulation of the detachment loads. If they uncover procedural lapses like missed torque checks or outdated ultrasonic inspections, the consequences could ripple across every MD-11 still flying. There's also the human side. The crew of Flight 2976 fought to the end. Voice recordings indicate calm professionalism, even as warning chimes sounded. They had mere seconds, yet their reactions likely prevented an even larger tragedy on the ground. For the broader UPS family, pilots, mechanics, dispatchers, the loss cuts deep. This is a company with a strong safety record. 0 previous engine detachment events and 1.2 million MD-11 flight hours. The organization has invested heavily in predictive maintenance systems, drone thermography, and data-driven safety audits. That culture may ultimately help investigators trace the flaw faster than in 1979, when much of the industry still worked on paper logs and gut feel. Every aviation accident changes the way we fly. After Flight 191, inspections became more rigorous. After TWA 800, fuel tank inerting systems became mandatory. And now, whatever the findings of Flight 2976, they will likely shape new inspection intervals, updated material standards, perhaps even retrofit kits, using modern carbon fiber reinforced composites to secure engines more reliably. Already, experts are discussing a potential switch from the current 7000 series aluminum to the 7500 series alloy, offering 20% higher crack resistance. Others propose software upgrades to the engine control unit that would detect subtle vibration patterns indicating a loose mount long before it failed. What gives this story its weight is not just the technology, but the continuity of memory. Every engineer who redesigned a DC-10 pylon in 1979 did so, hoping their work would prevent precisely this kind of recurrence. 46 years later, their lessons still stand, but time tests every design. Aircraft structures live lives of their own, absorbing stress, weather, and countless maintenance hands. The goal now is to translate those decades of accumulated wisdom into even more reliable oversight for the remaining fleet. As the wreckage of Flight 2976 was finally removed from the field, a quiet moment settled over Louisville. For the residents who watched the fireball that day, it was a shock. For the aviation community, a solemn call to review, not react. Flying remains among the safest human activities, precisely because each tragedy rewrites the rules. The challenge is ensuring those rules evolve as the machines age. When the NTSB completes its analysis, perhaps a year from now, its final report will detail the chain of events in forensic precision, metal by metal, second by second. But even before that document arrives, the conversation has already begun in hangars, flight schools, and engineering offices across the country. Pilots are reviewing abnormal engine separation procedures. Maintenance chiefs are revisiting pylon inspection intervals. And design engineers are asking whether modeling tools from 3 decades ago still suffice for aircraft now entering their twilight years. The MD-11 is a veteran workhorse. Many cargo carriers still rely on it because it hauls enormous loads efficiently. But the UPS 2976 tragedy reminds us that reliability isn't permanence. Every rivet, every mount, every inspection date matters. And in aviation, humility is safety, the willingness to believe that no system, however well proven, is immune to time. This investigation will take many months to complete, and the answers will come slowly, measured against evidence rather than speculation. Until then, all we can do is respect the process, honor those lost, and remember that progress in flight has always been written in lessons hard learned. I'm Conley, and I'll continue following the findings as they develop, helping explain not just what happened, but why. Understanding it makes every flight safer for the rest of us. In the days following the crash of UPS Flight 2976, the runway at Louisville International slowly reopened, though a sense of unease lingered in the air. Pilots who taxied past the scorched patch of Earth couldn't help but glance toward it, a silent reminder of how fragile flight can be. The freight schedules resumed, but inside every cockpit, there was quiet reflection, not fear, but respect. Respect for the men and women who lost their lives doing what so many of us do every day, trusting in the precision of machines and the diligence of those who maintain them. As investigators sifted through thousands of components, one theme began to emerge. Age. The MD-11 fleet, once the pride of intercontinental cargo operations, is aging. Many of these aircraft rolled out of Long Beach more than 30 years ago. Despite rigorous maintenance and modern monitoring systems, time changes metal. The structure doesn't fail suddenly. It evolves imperceptibly through millions of stress cycles. Aluminum, titanium, even steel, all have memory. Each takeoff and landing adds microscopic stories to their surfaces. Over decades, those stories compound into fatigue, and fatigue can eventually find the weakest link. The NTSB's Materials Lab in Washington, D.C. has become the heart of this investigation. Teams there are performing ultrasonic mapping and electron microscope analysis on fragments of the left-wing pylon recovered from Louisville. They're looking for striations, those delicate curved lines that record the growth of fatigue cracks over time. Each line represents a cycle, a takeoff, a landing, a pressurization. If they can count enough of them, they can determine whether the crack originated years ago or only recently. That answer will define whether the failure was mechanical, procedural, or perhaps even an undiscovered design vulnerability that has slept quietly for decades. In parallel, UPS and General Electric engineers are recreating the event in virtual simulations. They're modeling torque loads, airflow disruption, and the exact aerodynamic effects that would follow the loss of the number one engine. Modern computing allows them to replay the sequence thousands of times, changing one variable at a time. It's slow, meticulous work, but it's how truth in aviation is found, not in blame, but in physics. What makes aviation safety unique is that it doesn't rest on assumptions of perfection. It's built on redundancy, verification, and humility. Every time an incident like Flight 2976 occurs, the entire industry responds with a kind of collective introspection. Airlines audit their fleets, mechanics double-check torque records, engineers reread decades-old documentation looking for ambiguity. These responses aren't driven by regulation alone. They're driven by a culture forged through loss, the understanding that the next life saved may depend on the questions someone dares to ask today. There's a quiet but growing discussion within the cargo sector about the future of aging tri-jets. The MD-11 remains efficient for its payload, but maintenance intervals are stretching thin as spare parts become rarer and specialized technicians retire. Some carriers have already begun phasing in newer twin-engine wide bodies that meet modern inspection standards and burn less fuel. Yet, for many freight operators, the MD-11 is still an essential workhorse. It can lift over 200,000 pounds of cargo across oceans, land on shorter runways than most modern jets, and operate in diverse conditions. The decision to retire or extend its service life isn't just financial, it's emotional. This aircraft has built careers, delivered hope in disaster zones, and kept global commerce alive through pandemics and wars. Losing one feels like losing a colleague. For the NTSB, the goal is not to retire an aircraft type, but to identify the specific failure chain that ended Flight 2976. They'll examine maintenance procedures, inspection technologies, and documentation consistency across all MD-11 operators. It's likely they'll issue temporary advisories recommending enhanced pylon ultrasonic scans and non-destructive testing of load fittings. They may also suggest the introduction of real-time vibration sensors, small accelerometers mounted inside the pylons, that could alert crews if resonance patterns exceed safe thresholds. Some of this technology already exists on newer aircraft, but retrofitting older fleets requires investment and certification. Inside the UPS maintenance hangar in Louisville, where another MD-11 sits silently on jacks, mechanics have already begun voluntarily inspecting their pylons with extra care. These are professionals who take pride in what they do, and though they follow procedures to the letter, they also understand something deeper, that checklists are not walls but windows. They reveal where we must look harder. Each wrench turn now carries a little more weight. Among pilots, conversations have shifted too. Training departments are revisiting asymmetric thrust scenarios and engine-out procedures specific to the MD-11's geometry. Unlike twin-engine jets, tri-jets respond differently when one wing engine fails. The centerline engine can mask some yaw, but also introduces its own aerodynamic quirks. Understanding those subtleties could one day make the difference in a marginal situation. None of this is about casting doubt on Flight 2976's crew. By all accounts, they did everything possible. It's about ensuring the next crew, somewhere in the world, inherits every lesson learned. For families of the lost crew members, the coming year will be one of long waits and technical jargon. NTSB reports are not emotional documents, they are scientific autopsies of machinery. Yet behind every number, every PSI, every degree, every second, are real people. Colleagues who shared night shifts, engineers who built trust over coffee and deadlines, families who checked weather updates just to know their loved one's route. The aviation community often calls itself a family, and it's in tragedies like this that phrase becomes literal. Support networks quietly activate pilots, fly in for memorials, mechanics wear black armbands, and across thousands of miles, the message circulates: they were one of ours. There's comfort in knowing that accidents like this are exceedingly rare. In a world that sees more than 100,000 flights a day, an event like UPS 2976 is an anomaly not because of luck, but because of decades of learning built atop every previous tragedy. The systems that will now dissect this event are the same ones that have made air travel the safest form of transportation known to humanity, and in that sense, even the darkest night contributes to the dawn that follows. Months from now, when the final NTSB report is released, it will likely contain new mandates, perhaps new inspection intervals, or material requirements. Maybe it will recommend a pylon redesign, maybe it will conclude the failure was singular and contained. Either way, the takeaway will be the same: vigilance never ends. The lessons of Flight 191 inches 1979 were not forgotten. They were transformed into new engineering standards that made flight safer for generations. Flight 2976 will continue that lineage, a reminder that no matter how advanced our technology becomes, safety is a living process, one that evolves with every rivet, every inspection, and every ounce of human attention. As dusk settles over the Louisville airfield once more, cargo jets continue to rise into the amber sky. Each one carries not just freight, but the legacy of everyone who has ever touched the world of flight pilots, mechanics, designers, and investigators alike. The runway lights guide them into the distance, steady and unwavering. That's what aviation has always been about: resilience, responsibility, and renewal. To those who were lost aboard UPS Flight 2976, your final flight will not be forgotten. Your story will help protect countless others who take to the skies. And for those of us who remain, the ones who keep these machines aloft, your memory will serve as both a warning and an inspiration. This is Conley, thanking you for taking the time to understand what happened, and reminding you that every answer we uncover brings us one step closer to ensuring it never happens again. Good night, and fly safe.